Hello and welcome to this presentation on time waveform analysis, a whole new insight into your machine's health. My name is Jason Tranter, the founder and managing director of Mobius Institute. Now, that is actually a curious name for this presentation because in actual fact, time waveform analysis isn't a new way of analyzing your machine and understanding its machine's health, the machine's health. It's been around for a long time. The trouble is not enough people use this technique. So hopefully through this webinar, through this presentation, we will demystify some of the issues related to time waveform analysis, and hopefully you'll feel comfortable using it much more. So I'm briefly going to talk a little bit about spectrum analysis versus time waveform analysis and why therefore you need time waveform analysis, and then we'll talk a bit about how to measure the time waveforms properly and how to analyze the time waveforms. But just briefly, I do a lot of these webinars and presentations, and I don't often tell people what we actually do at Mobius Institute. So basically, we provide training in two forms. We have a lot of e-learning training, but lots of classroom training as well. In the area of vibration analysis, we actually have training centers in about 55 countries. We at this time train about 3,000 people a year. We have trained over 17,000 people just in vibration analysis, just in those classroom training courses. We also have e-learning in that same area, and on the reliability improvement front we have a product called iLearn Reliability. It's all e-learning at this particular point in time, and it is there to sort of paint the much bigger picture of reliability improvement. But all of our vibration training follows the ISO standards, and our certification process is ISO accredited, as in it's accredited to ISO IEC 17024. It's equivalent to Vibration Institute, it's equivalent to BINDT. Anyway, we've got training centers all over the place. I happen to be located down here, that's the head office of Mobius, but we have offices in the United States, Central America, and in Europe, in Belgium. Anyway, let's get on with it. We train a lot of people, as I just mentioned, and I give a lot of presentations and some of those courses, and I often get to talk to people about what they do with their vibration analysis. And when asked about time waveform analysis, I normally get one of three responses. One, I get people, time waveforms, do I really need them? Well, I'm here to tell you that yes, you do. I also get the response, well, we might have tried them but didn't find any use, and the settings are too confusing to use it properly, so hey, I'm just happy with spectrum analysis. Well, I hope to convince you that yes, spectrum analysis is a great tool, but time waveform analysis provides a very useful view of what's happening inside your machine. And unfortunately, in a small number of cases, I get, yes, I always use time waveform analysis. And we high five and say it's a great idea, and we move on. But in reality, you don't need time waveform analysis unless you monitor machines with rolling element bearings, which is probably quite a few of your machines. And unless you monitor gearboxes. Boy, if you're monitoring gearboxes without time waveform analysis, well, you should be. Let's just say you should be using time waveform analysis, because as those teeth mesh together, any little change in the surface of those teeth, particularly if there's cracked teeth or broken teeth or anything like that, it will show up very clearly in the time waveform, for sure, much clearer than in the spectrum. If you monitor pumps and they can have flow-related issues, they will show up clearly in the time waveform, and yes, there'll be changes in the spectrum, but the time waveform is the truth. It is exactly what happened inside your machine. The spectrum, that's just taking a whole lot of time waveform data and mushing it into one view of that data. Yes, mushing is a technical term, but that process loses a lot of very useful information about what actually happened. Or of course, if you see harmonics or sidebands or a raised noise floor, if the bottom of the graph lifts up, there's a reason for it. The spectrum is showing you those harmonics and sidebands and raised noise floor because of some important changes in your waveform. So go and look at the time waveform and find out why. So, you have to ask yourself the question, why do you perform vibration analysis? You're trying to detect if a fault exists, and hopefully through the spectrum you'll do that, but that's not even guaranteed. You can have problems and not know it just by looking at the spectrum. You certainly want to diagnose the fault. You want to know what the nature and severity is of the fault, and time waveform analysis will give you both of those pieces of information. And time waveform analysis in particular is very good at giving you an idea of what the severity of the fault is. And you need to determine the action plan. Does maintenance need to be performed? Do we need to replace a component, overhaul a component, change the way the piping's set up or the flow, and whatever the case is, time waveform analysis helps you do those things better than using spectra alone. The way I look at it though, when you start thinking about time waveform analysis, you've really got to use both sides of your brain. You've really got to think about these two forms of analysis in two different ways. When we just think about spectra, we're using one side of our brain, and we think in terms of how the settings of our analyzer affect the spectrum. So, for example, here are two spectra. As you can see, they're from the same machine, but this one has a higher Fmax. Well, of course, if I don't choose an Fmax that's high enough, I won't see these peaks in the spectrum. But, of course, the higher and higher you make the Fmax, the lower and lower your resolution is, and which, of course, can be corrected by increasing the resolution, but the higher the frequency is, the more and more those key sources of vibration, 1x, 2x, 3x, 4x, up to 10 to maybe 15x, all get scrunched down one end of the spectrum. So you can have a very long spectrum with a very high Fmax, but there's a lot of really important information down at the lower end of the spectrum, and you therefore have to zoom to see it. But you may not zoom. You may not think you have to zoom. And if you're analyzing a lot of data, that adds a lot to your work. So you need to choose the Fmax setting correctly and think about using two spectra. I'll talk a bit about that later. The point is that in your mind, probably the Fmax setting is all about making sure we don't miss any data. But it has an important effect on the time waveform, which I'll get to. Likewise, when you think about the lines of resolution, 800 lines, 1600 lines, 3200 lines, and so on, you should know that that enables you to see the same spectrum, as in with the Fmax, more clearly. So here you can just see a bit of the spectrum there, and the peaks look kind of broad. In reality, there are lots of sidebands, and that would tell you something about the nature of the fault. This might have broken rotor bars, for example. So lines of resolution is also important. And when we think about it in frequency terms, all we're really thinking about is the resolution we get, not so much what happens with the time waveform. But it has a very important effect on the time waveform as well. And when we think with the spectrum side of our brain, we also have to think about the units, displacement, velocity, and acceleration. With acceleration, I get to see more of what's happening at the high frequency end of the spectrum. Velocity, I can actually see some peaks there. I may not, but there's less emphasis here. But the trouble with acceleration is that at the low frequency end of the spectrum, it tends to suppress or reduce the relative amplitude. The information is there, it's just less obvious, whereas the velocity, it's higher. But again, from a frequency point of view, that's the effect I'm having. Just what am I going to see in the spectrum, and how much emphasis is there on the low frequency versus high frequency. With the time waveform, it's quite different. With a time waveform, it allows us to determine or detect when there are impacts and rubs and things which tend to generate more high frequency vibration. When there's impacts and very short duration effect, we want to see that in acceleration. A velocity tends to show us more the low frequency information. So what we do know is that if I see a spectrum and it's dominated by, a 1x peak, as you can see in this case, then I feel fairly comfortable that the vibration is primarily at 1x. And if you look closely at this rotor here, there happens to be some unbalance, and that's why we're seeing this in the spectrum. If I look at the time waveform, you notice it looks pretty much like a sine wave. Now, it's not a sine wave. The fact that there are these flat parts and odd shape means that there is more to the vibration than just a sine wave, and you can see these little harmonics here. But the fact is, I might personally look at this in logarithmic format and I would see these harmonics more clearly, but the bottom line is, when you see a spectrum that is primarily dominated by 1, 2 or 3 frequencies, I can relate those peaks back to something that's rotating inside the machine, teeth meshing together, pump veins going through the fluid, unbalanced, whatever. And the spectrum gives me a pretty good idea of what's happening. As soon as I start seeing harmonics and sidebands, that's when I know there's more going on and the time waveform becomes more important. And just to quickly recap, when I think about the way the FFT process works, we know that, for the once per revolution vibration, like unbalance, we can think of that as just a single frequency. And depending on the speed, the frequency obviously changes. Same with the fan blades, that swooshing through the air, we get a certain amount of vibration. And that is just one frequency. Now, I'm going to, just for simplicity, say, well, yes, the bearings generate a vibration. In reality, it's not a nice sine wave like that. The point I really want to make is that when we look at those 3 sources of vibration here, we can clearly relate those back to the machine, but what we measure is something more complicated. That is the time waveform. And in a situation like this, looking at this time waveform kind of complicates things. What I really want to know is just what those 3 frequencies are, and that's what the FFT is. So if we rotate this around, we see we've got 3 frequencies, and if we rotate it all the way around, there are my 3 frequencies. And I've got the 1x peak. I'll just make that amplitude a bit lower. There's my 1x peak. There's my peak related to bearing frequencies and my peak related to the blade pass frequency, all measured from this one point. This isn't an explanation of the FFT process. The point I really want to make is that when you've got nice simple vibration like that, like we saw just a moment ago, we therefore have a nice simple spectrum, and in that instance the spectrum is giving you all the information you really need. It's when we see distortion in the time waveform, when the motion of the machine and the shaft and the bearings isn't just smooth, simple harmonic motion, that's when we do need to look at the time waveform, because what we see in the spectrum is much more complicated, and if you like, it's due to the FFT process. There's a lot we could say about that statement, but let's just leave it at that. So if there's impacting or rubbing or modulation or anything else that's going on, the spectrum becomes more complicated, and that's when you need to look at the time waveform. And here is just one example, and we'll come back to this one later actually, but here I have all kinds of harmonics. Now if you've been doing vibration analysis for a while, you can look at that spectrum and say, hey, I know that it's probably looseness. And there's the time waveform. We see a little bit of motion in one direction and a lot of motion in the other. This is what the sensor mounted on the machine felt from one split second to the next. It had a little bit of motion and then a big spike of motion, a little bit of motion, a big spike of motion, etc. This is what happened from moment to moment to moment. Now when we take all of that and do an FFT, and maybe we do that a few times and average it, this is what we get. So this is taking all of this detail and mushing it together and giving us just this one spectrum. Now you can see there's some variation here, but probably that variation as we go through time isn't in this instance the really important piece of information. The fact that it's non-symmetrical tells me that there's more movement in this direction than that direction, and that helps you a little bit with the diagnosis. But we'll see other examples where the time waveform is even more useful. In this instance, if I was looking at a spectrum, I might see these sidebands. Now I can tell there's amplitude modulation, possibly frequency modulation, but let's just say amplitude modulation. And you know, when I look at this, the time waveform itself, this is the truth of exactly what happened from moment to moment. The vibration rose up, the vibration went down, the vibration went up, the vibration went down. And that's why we have sidebands, because when we see amplitude modulation, we get sidebands in the spectrum. But this gives me an idea of exactly what was going on. You know, is it just short peaks, short spikes, or longer spikes like this? You know, what actually happened? The time waveform tells me. So, having had a quick glimpse at those time waveforms, let's now put the let's start tuning the time waveform side of our brain. Now, I think the first thing that perhaps I need to convince you of is that the time waveform is really telling us something that we didn't know in the spectrum. Hopefully from the examples I've already convinced you of that, but let's look at some more examples. So here again is a time waveform, and this is what's happening from moment to moment to moment. We've got a bit of a spike, another spike, a bigger spike, a smaller spike, and you can kind of see this pattern repeating as time goes on. Now this is a damaged bearing, and all of these little spikes are the balls as they roll around on the inner race, going into the load zone, out of the load zone, into the load zone, out of the load zone. But I can see what's happening in and out of the load zone. I can see what sort of amplitude the spikes are. I can see that this is up to 8 Gs, and that gives me a very good indication of the severity. Remember, this is the truth of what happened. This is the actual force of the impacts that the sensor felt. You know, that's something to remind you of, that the vibration has to get from the bearing up to where you mount the sensor. It's critically important, therefore, that you mount it properly. But this is like a little movie recording of exactly what happened inside that machine, and I can get a sense for how severe it was and everything else. But I will just say to you, notice something about this time waveform. You know, I can see these spike, spike, spike. You know, this is a useful time waveform. I can see, you know, a number of these impacts. If I had lots and lots and lots of these impacts on this graph scale here, it wouldn't be very useful. If I only had 1 or 2, it wouldn't be very useful. So it's just part of the message that we'll get into in more depth. In this case, this is also damage on the inner race of a bearing. It's also in Gs, not as severe. But notice the nature of this vibration looks quite different. You know, if I look at that, there's big sharp spikes. Not so in this case, and one that we saw just earlier. But it all gives me useful information in addition to the spectrum. Here's another case of a bearing fault. We can see it's sharp spike, not so sharp spike, sharp spike, not so sharp spike, etc., etc. Again, this is starting to tell me what is happening inside my bearing. Now, you may be thinking, what do I care what's happening inside my bearing? I know it's damaged. I need to, schedule a replacement of that bearing. But in certain cases, particularly where that bearing is more critical, if it's, for example, a high-speed machine and you know you've got less time to react, or it's a critical machine and it's very important that you make this decision correctly, this is where you really, you need every piece of information you can get so that you can make an accurate diagnosis. If it's a small, inconsequential machine, then just seeing the peaks in the spectrum may be enough, but usually in your software you can press one button, you'll see this time waveform. It takes just a couple of seconds to tell whether it's actually giving you useful information or not. Okay, here's another case, but it's slightly different. Number one, you can see actually the damage in the bearing, but this is a peak view time waveform. This is where we've taken data from a higher frequency vibration source, kind of like ultrasound, where we just listen to the higher frequencies. We transform the data so that it looks like lower frequencies. But peak view data captures the peak spikes with a high sample rate, makes everything positive going. So that's why these time waveforms only go up and they don't go down like the ones we've seen before. In any case, we don't have time in this short webinar to explain as much as I would love to, but bottom line is it is a time waveform, and everything that I'm talking about time waveforms applies to peak view, shock pulse, spike energy, envelope, demod, and any other high frequency technique just as much as it does if I was looking at just the raw vibration from the accelerometer, and if you're looking at fluid film bearings, from the displacement probe as well. Okay, here's one we looked at before. I can see the impacts. I can see the harmonics, but now I can see the impacts, and I can see how severe it is based on the level of the G level. This case is from a damaged belt. Every time that damaged area went through the pulleys, we got a spike, 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 spike. And again, that just gives me some information about the nature of the fault. Here we have cavitation, and the spectrum gives me an indication that there's cavitation. The sound the machine made when I was collecting the data gave me an indication if I was listening properly. But here we can see these pulses, these surges in the vibration, but this time they are not periodic. The space between it, and therefore the time between each one of these spikes of vibration, is not the same. Therefore it's non-periodic, and that's what cavitation does. This gives me an idea. This tells me exactly what's going on. Gears meshing together, the lower speed gear mesh, 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 mesh. There's misalignment in this case. Here's the pinion, mesh, mesh, mesh as it's rotating around. Yes, I could see sidebands in the spectrum, but you probably know that you can see sidebands for a whole lot of reasons with gearboxes. And yes, we can look at the 2x gear mesh and 3x gear mesh and all those shenanigans. Bottom line is that the time waveform can often tell you much more. Here's a great example. So we have a gear wheel here with a whole lot of healthy teeth but two damaged teeth. Well, this spike we see occurs when these damaged teeth go through the mesh, as you can see here, 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 etc. All the lower amplitude vibration you see between the spikes is when the healthy teeth are going through. So there's a big spike and sort of response, big spike and response, and so on. And that's basically once per revolution of this gear. It's 1x vibration, it's not gear mesh vibration. So yes, we could look for 1x going up, but then we have to think about what that means. This tells me exactly what's going on. Another case from a gearbox, mesh, 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 normal, bad tooth, bad tooth, bad tooth, bad tooth, maybe another bad tooth, maybe not so bad tooth, but different. So you can see these 4 spikes, 1, 2, 3, 4, 1, 2, 3, 4. There's 4 bad teeth and maybe a 5th when there's that spike. So that's the 4th and that's the 5th. But again, notice the time scale. I'm not seeing, 20 revolutions of the shaft. In this case, I'm only actually seeing just a couple. But, it's important to get those settings right. And this vibration you might look at and, oh, gee, what's happening here? It looks like it's high amplitude, looks like a real serious problem. But in actual fact, we look at the G level and that's not getting my attention. We're looking for periodicities. I'm not saying that right. Anyway, you know what I mean. Anyway, basically this time waveform's pretty boring, which means it's all smooth, which means it's not telling me anything new, so I just move on. That gets my attention. That doesn't. 2 seconds later, I'm moving on. Here's an interesting case where, okay, maybe there's some misalignment here or bench shaft or something, 1x and 2x peak. Nothing else much going on. Took a quick glimpse at the time waveform. Oh goodness, plus or minus 10 Gs. What's that all about? Switch to acceleration. Aha, there was an indication in the spectrum, but because I looked at it in velocity, had no idea. So the G is just a quick glimpse. There's nothing particularly periodic that I'm seeing here, but it's high level, which would suggest to me there might be a lubrication issue there. Just a quick switch across to time waveform told me that, and that's information I didn't know before. So how do we measure these time waveforms so that I do get useful information? The fact is, you are measuring them now. Sometimes people think, oh, I don't want to have to take another measurement. I don't want to be out at the machine any longer. Well, number one, you're measuring them now. It may turn out that the settings you're using aren't ideal. We may choose to take an additional measurement, but I guarantee you it will not take long. Seconds, that's it. The fact is, you are measuring them, you probably just aren't saving them. There's probably a setting somewhere where you just check a little box, yes, keep the time waveforms. Check the box. Okay, the trouble is, as I just mentioned, the settings may not be ideal. The time waveform you can get by default may not reveal as much useful information as you would like. So, through this little session, of course, again, this is just a brief summary of all these things. Our training goes into much more detail, but let's see if we can understand the settings if you're not already familiar. Now, the fact is, our analyzer, when you press the go button, it has to digitize an analog signal. Now, I don't want to turn this into a detailed signal processing lesson, but the fact is, unfortunately, to get time waveforms right, I'll propose a couple of rules of thumb, but it really does help if you understand what's happening in the analyzer. Now, what I'm looking at here is if you were to look at the signal or the voltage that comes out of your power outlet, whether it's 110 volts, in the US, or 240 here in Australia, that's our plug, 220 in Europe, 220, but that's 50 hertz, that's 60 hertz, 50 hertz, whatever it is, we've got this analog signal. It's a voltage. Stick your finger in, it goes zap. So don't stick your finger in. But that's actually the RMS level that we talk about. Now, if we want to digitize that, we've got to turn that into a series of numbers that represents that sine wave. So we can switch our little analyzer here, our little voltmeter, so that at the moment it's taking a measurement 60 samples per second. So I'm just coincidentally, I'm grabbing it right on top of the cycle, which isn't actually giving us any useful information. So what I'm going to do is increase the sample rate. So now you can see it's converting the instantaneous voltage into a digital value. There's one there, one there, one there, one there, and these are samples. All I'm doing is converting the actual voltage into a digital number that we can then use. But each time I click this, it digitizes a bit more quickly. Takes more samples, more of those green dots per second. And if I join all those green dots together, you can see that the green graph looks quite a lot like my red graph, which is the analog signal, which is good. That means what I've got to analyze is pretty good. But the samples per second setting that I'm changing here relates to the F max in the spectrum, and you'll see more about that in a moment. The number of lines of resolution in the spectrum determines how many of these green dots I'm going to get, how many samples. The higher the lines of resolution, the more of these green dots I'm going to collect, which means I'm looking at a longer time waveform. It means the shaft turns more times, and that can be a good thing, it can be a bad thing. So let's explore this just a bit further. So the other thing to understand is that when you tell the analyzer, for example, that you want, let's just keep it simple, an 800 line spectrum with just one average, let's just say, what the analyzer does is it's going to digitize that. It's going to grab, it happens to be 2048 numbers at a certain sample rate depending on the Fmax. Let's just focus on the measurement process here for a second. So it's going to grab a chunk of the time waveform, it's going to record that, and then it's going to say, okay, make a spectrum out of that. If we had 2 averages or 3 averages, it's going to do it 2 or 3 times. Make a spectrum, make a spectrum, make a spectrum, and average it together. What the analyzer does though, if you check the box to say, yes, I want the time waveform, it will either keep this time waveform or that time waveform. To the best of my knowledge, none of the analyzers will keep the whole, in other words, the 3 of them all together. It'll just give you either the first or the last. So you're only recording, keeping this information, and then that's what you can analyze later. And you know, if you use overlap, then there's overlap between those. But in either case, these are the time records, and this is what it's going to keep. The settings you chose are probably optimal for the spectrum, not necessarily optimal for the time waveform. Now again, I don't want to go into too much nasty detail, but the Fmax setting, which is, you know, the number of hertz or CPM that you collect, relates to the sample rate, the number of samples per second. In fact, if I multiply the Fmax in hertz by 2.56, I get my sample rate. If I the sampling frequency. If I say 1 divided by the sampling frequency, that is the time between the time waveform samples. So remember before we had those little green dots? It's the time between those samples. And that tells us everything about what we're going to collect in the time waveform. If I'm looking at events that happen very, very quickly, you know, one tooth going through the mesh, one ball rolling along and hitting this small spall, I want just a little bit of time between those green dots so that I can capture that information. So that's one thing to understand. The Fmax controls how much time there is between each of those samples in the time waveform. The lines per resolution, how many of these values I have in my spectrum dictate or determine how many of these samples I will see in my time waveform. So the lines of resolution might be 800, 1600, 3200, etc. And correspondingly, the number of samples, which is often represented as n, is 2.56 times this number. So if you had an 800 line spectrum, you will have 2048 samples. And that therefore determines how long the time waveform will be, because the resolution, the frequency delta between each of those 800 or 1600 or 3200 numbers in the spectrum determines how long the time waveform will be. Now this is a 2-second time waveform. 1 divided by 2 means that there's 0.5 hertz between each of the values in my spectrum. So look, this is something that may be making your head spin right now. If you're new to vibration, best thing you can do is wind it back and hear it a couple of times, or of course go to a training course. But anyway, it's the point I'm really trying to make is that these settings that you choose for the optimal spectrum affect the time waveform we get, and you have to understand that. You may in your analyzer have the ability to just directly set the time waveform settings in terms of time or numbers of revolutions of the shaft and the time between samples. You have to look at your analyzer, but probably not. Okay, so now what I want to do is bring this home and start relating it to a real machine. So here's my shaft turning, and because of the Fmax setting, which is the number which relates to the number of samples per second, that determines how much time how much the shaft rotates between each time we take a digital sample. So the higher the F max, notice what happens. Number one, obviously, as I change the F max, so I'll just change that to hertz, and I increase the F max, that means it's 1000 hertz. Notice what happens. Watch the time waveform and watch the spectrum. As I increase the F max, notice what happens. As I decrease the F max, or as I increase the lines of resolution, or I decrease the lines of resolution. The lines of resolution doesn't affect the range of the frequency, but it does affect either how many revolutions we see or how many seconds we see. Same deal. So as I increase the lines of resolution, I take, as I go from 400 to 800, I double the amount of time that I'm collecting data, and therefore instead of 20 revolutions, I see 40 or 80. Now this time waveform is not very useful for me. I'm seeing too many revolutions makes it harder to analyze the time waveform. So there's just that relationship. It's a keen one to get into your mind. The lower the number of lines, the better the time waveform looks, the clearer it is. But the sample rate determines how many samples I get. I'm going to talk a bit more about that in a second. So, how do we measure the time waveforms correctly so that we get good settings? Now, going back to a little bit of theory, but Harry Nyquist once said and proved that you only need just over 2 samples per cycle, like the whole sine wave of a particular frequency, in order to see that frequency in a spectrum. Now, in our industry, we use 2.56 instead of just over 2. We use 2.56, and there's a long story why that is. Now is not the time. So we use 2.56, but all Harry needs to see the peak in the spectrum is just over 2. But just over 2 does not give us a very nice looking time waveform. It's very coarse. It's enough for the FFT process. It's not good from a time waveform. Because if we had just, more than 2, so now I've even got, 1, 2, 3, 4. That's just on that side. So I've got basically 4 samples per cycle. If I go from here to here as one cycle, I've got 4. And this green line we're seeing is the digital version of the sine wave. Those 4 samples are well and truly enough for us to have that appear in a spectrum. If this is a particular frequency, then that peak will appear in the spectrum. If I want a better representation of the time waveform of that sine wave, then I want more. Now that green wave looks like the original analog blue wave. Now in the case of sine waves, a simple sine wave like that looks pretty clean and simple, but still when I'm doing time waveform analysis, I want the waveform that I'm looking at to look kind of like, or very like, the original analog signal, which was telling me what was happening inside the machine. Now, I personally like using the analogy of the movies. So here's Steven Spielberg, a movie maker. Think of time waveform analysis like making a movie. So here, now, to make this movie for you, as in this recording that you're looking at, unfortunately what the computer's doing right now is taking frame of what I'm seeing on the screen. So I'm seeing one thing, you're seeing something slightly different. The point is, here is a movie we're trying to make, or we're looking at. And I needed a certain number of seconds in order to see this surfer zooming along this amazing wave called Chapu. I happen to like surfing. Before he crashes and gets ripped over the top and into the reef. Not nice for this surfer. But he knew the risks. So, from a movie point of view, I need a certain number of seconds. If I was filming the petals opening on a pretty little flower, obviously I need more than a few seconds. If I want to film a bullet smashing through glass, clearly I probably only need a couple of seconds to film that. So number one, you have to climb inside your machine with your imagination and think, how long a recording do I need to see what I want to see? And this is one of the keys. You have to understand the failure modes. You have to understand what it is you're looking at. How long does it take for a tooth to go through the mesh? How long does it take for those balls to roll over the damaged area of your machine? This is us using the time waveform analysis side of our brain. Forget frequency. Just forget it, okay? We're in the time waveform analysis mode. We're in movie making mode. Now, let's get back to our little movie here. The point is that a normal movie camera actually films at 24 frames per second. Just like I talked about samples per second, here we've got frames per second. What I'm going to do is slow this movie down. What I hope you can see is that it's very jerky. It goes, frame, 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 frame. Now our eyes couldn't really see that before at full speed, but now doing my time waveform analysis, if you like, I'm watching this surfer much more closely. Now, what I'm going to do is, instead of looking at this in slow motion using 24 frames per second, I'm going to use 555 frames per second. And I hope you can see it like I can see it. It's beautiful and smooth. There's no jerkiness. I can see exactly what's going on. Now you may argue that I don't really need to see it, but hey, it's a good example. So here he is, he's surfing along and he's thinking, I'm going to make this, I'm a hero, this is excellent. It's like, oh no. He splats against the wave, great force. You can see his kidneys squeezing out there. He's crashing along. The reality, and there's his arm. He waves to his mother, Mama. So here he goes again. He's making it. He loses control. Oh no, splat against the wave. He realizes he's going to go smashing into the reef soon, and he waves, Mama. Yes, anyway, and he's going to get wiped over the top and into a shallow reef. Anyway, so now one of my rules of thumb, which there's no ISO standard about this, unfortunately, and different texts might describe it differently. But as far as I'm concerned, you need at least 10 samples per event that you're looking at. You want to see 10 of those frames in the movie, if you like, to really see what happened. More than 10 is better, but I would say 10. So if you were analyzing, gears meshing together and you were concerned about damaged teeth or something like that, well then you want at least 10 samples while a tooth is going through the mesh, so that you can see it clearly in the waveform. So here's our simulator again. What I'm going to do is say, let's make it look like a gearbox. So now using 500 500 Hertz F max, with this rotating at 25 rotations per second, 25 Hertz, you can see where we are taking samples relative to the teeth. So now you can see that I'm only getting a few samples per tooth mesh. In fact, I can put this into movie mode. So from our movie point of view, this is what I'm seeing. It's this sort of jerky motion. So yes, I can look at it from a time waveform point of view. There I am zooming in and I'm seeing that I'm only getting a few red dots on each cycle as the tooth meshes. But if I broke a tooth, let's watch what happens when this broken. I know it looks a bit silly, but anyway. When it goes through the mesh, do you think I'm going to be analyzing this properly? Let's look at what happens. There's the spike, and I've only got a couple of points on that. That's not ideal. So if I instead crank up the sample rate, now when this goes through the mesh, you can see I'm getting lots more red dots per tooth. And when it goes through, I'm digitizing this event much better. When I go into movie mode, you see it's much smoother motion. I could even go higher and higher and get very smooth motion. So look, there's lots of things we could talk about here. We've only got a certain amount of time. I really just want to impress upon you that in most analyzers, it's the Fmax setting that dictates how many samples per second and therefore how many samples per event I'm actually capturing. Now, the other thing that I want to do though is not capture too many teeth meshing together during my measurement, too many rotations of the shaft. Now, and it's the lines of resolution setting that do this. So my rule of thumb, yes, here's my thumb, saying this, haha. I use my lines of resolution setting to control how many revolutions of the shaft, in essence, I'm going to see. Maybe in your software you can, if you've told it the running speed, you can set it more directly, but normally it's be your lines of resolution setting. If you were doing a gearbox, if you're analyzing a gearbox, then I would say that if you set your Fmax at, somewhat above 4 times gear mesh frequency, and I would use greater than, say, 4, and a quarter, 4.25 times gear mesh frequency. That means all the sidebands would be visible in the spectrum. That will give you greater than 10 samples per tooth mesh. If the Fmax was the gear mesh frequency, 4 times the gear mesh frequency, you would have 4 times 2.56 samples per tooth mesh. Now that might be all a bit confusing. I need much more time to clarify that. But anyway, if I go over 4, that means it's 4 times 2.56, which is 10 point something, and that would be good. We go a bit higher, then the spectrum looks good. If I want to get 4 revolutions of the shaft, that's why I would say that the lines of resolution has to be 16 times, or greater than 16 times the number of teeth. Anyway, just a simple rule of thumb. And so this is what we're doing here. If I look at this again and I crank this up, so I can crank up my Fmax to being more than like the Fmax divided by gear mesh frequency is 4.6 in this case if I use 1500 Hertz, and now we can see that I've got lots of red dots. I've actually got more than 10 red dots per tooth mesh, which is ideal. But here I've got an interesting challenge. Look at how many revolutions I'm seeing. I'm actually seeing, almost 7 revolutions of the shaft. Multiply that by the number of teeth mesh, and it's not really ideal, is it? I could go down in lines of resolution to 200 lines of resolution to give me the time waveform I want, but the spectrum's not very good now. The spectrum has rotten resolution. If I crank up the lines of resolution, now my spectrum looks good, but my time waveform doesn't. And this is a classic case. I'll talk about this a little bit more in a second. This is a classic case where you might actually want to take 2 measurements. One so that you get a good spectrum and an okay time waveform. Still keep the time waveform. It's always good to have the time waveform that matches the spectrum. And another spectrum. So I can either crank this down or better still crank that up to get the time waveform you want. Just crank that up. It means it's a very, very fast measurement, very, very high resolution. Let's look at the movie. Oh, beautiful and smooth. Oh, look, I can see exactly what's happening. Okay, so crank it up. Okay, so some suggested settings. Look, I personally am a proponent of using 2 spectra. One that focuses on just the first 10 orders, 10x of shaft turning speed. Enough resolution so that you can clearly see all the sidebands. You may even go to 3200 lines of resolution. Now the fact is, if you keep the time waveform, you will have lots of revolutions of the shaft, which isn't good for looking at the details, but it's great if there's any beating, modulation, cavitation, these sorts of things. That's a great time waveform for that. On the high frequency side, I might set an Fmax that's 100, 150 times shaft speed, and just lower resolution, which, a lot of times the additional information you get from this high Fmax measurement, you don't necessarily need a lot of resolution. You can use fewer time averages. The higher you make this, the lower you can make that, but it's going to dictate what you see in the time waveform, as I've explained. But I would use units of acceleration for this one because this is where you're picking up the high frequency information. Now for gearboxes it's a little bit more complicated, because if you went, and I just explained it really, if you go, say 4.5 times gear mesh frequency, now the spectrum looks okay. I've got a high enough sample rate to have more than my 10 samples per gear mesh, but I want a low resolution in order to get a time waveform that's okay, but my spectrum's not good. So I would tend to go even higher than this, so that I've got a lower number of revolutions and a higher number of samples per tooth, but the spectrum won't be very good. That's fine. That gives me a really good time waveform. And then, hey, crank up the lines of resolution. Still go with your 4.5 times gear mesh frequency, higher resolution, so I can easily see the sidebands around the gear mesh. Anyway, like a lot of these things, we need more time to talk about them to to really drive these things home and explain everything, but that's why we have training courses. Now, how do you analyze this information? Okay. First point that I could have made much earlier actually is that one of the comments I hear when I say, oh, collect time waveforms, people slap their forehead and said, oh no, I've got more data I have to analyze. If I collect it, I have to analyze it. Well, that's not true. If you collect it, you can analyze it. If you don't collect it, you can't. So just because you collect it doesn't mean you have to do some exhaustive analysis. If you collect it properly, then generally you can look at a spectrum, you find out from your software how you can press probably just one key to look at the time waveform, and you could take a 2-second glance. If it looks boring, move on. If it looks interesting, analyze it. And it's as simple as that. If you collect it properly. If you don't collect it properly, they will probably all look boring and useless, and therefore you'll conclude that it's not useful information. It's just because of the way it's being collected. So, on the other hand, you can wait until your spectrum shows some harmonics and sidebands and the noise floor lifts up, and then you can look at the time waveform. It's useful to have historical data, so I would always say look at it all. But basically, if it's boring, move on. If it's interesting, let's look at it more closely. The other thing you can do is if you trend crest factor. Now, crest factor is the ratio of peak to RMS, and if we just look at this very simple case, here's a simple sine wave. So the peak or peak to peak has a fixed relationship to the RMS value. If I increase the amplitude, the ratio of those two numbers doesn't change, so my crest factor doesn't change. But if I have some spikes, now let me just tweak a couple of things here, and I create some spikes. Well, see here, I've got bigger spikes. That has a much greater influence on my peak and peak to peak value than it does on the RMS. The RMS isn't changed much by just having a few spikes. Now, if I have more spikes, the RMS changes more. But the bottom line is that when I just get a few spikes relative to the amount of normal vibration, the crest factor will trend up. And when you see that, that's another warning sign. Look at your time waveform. Okay, so I've already mentioned, yes, acceleration is good, but you might find that if you ask your analyzer to give you a velocity spectrum using analog integration, you won't have an acceleration time waveform. You may, if you use digital integration, you need to look at your analyzer to see how you're going to do it. But of course, if you use the high range spectrum in Gs, you will have Gs in your time waveform. If you set it up properly, you won't need to zoom. If you need to zoom, chances are you will miss things because you're not going to zoom on every single time waveform. So you need to look at that. The x-axis can be time or revolutions, and I think I showed that before. And we'll have a look at some other things that we can use. But remember though that we can be looking at normal time waveforms, also time waveforms from peak view and enveloping. In here, this isn't the same from the same machine, but this one's in Gs that we saw earlier. This one is in velocity, and you can see more of the once per revolution vibration in there with the bearing spikes superimposed on top. If the severity is not great, we may not see them superimposed on top of a velocity time waveform. It's the acceleration where they're going to stand out, because the once per revolution does not generate much acceleration vibration, so it only enhances the high frequency impacts. Okay, but when I am analyzing a time waveform, you will hopefully find that your software will let you create markers that are separated by the 1x frequency or the bearing frequencies or whatever you should be looking at, depending on your machine. If not, you can look at these spikes. You see spike, 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 spike. You can look at the time difference between them. That's the number of seconds at this one, the number of seconds at that one. The time difference, 1 divided by that time difference, is a frequency. And then you can relate that back to your machine to see that that corresponds with your inner race frequency. If that was confusing, just play it again. Hopefully I've said it all. So, how else can I look at those time waveforms? Well, the circle plot is useful. It's easier to see it than explain it. Here is a normal time waveform, which, okay, it tells a good story. There's modulation going on here, and I can see something in the spectrum. But I can wrap that around a circle. Now, remember, the machines rotate, and we are interested in what happens. Sorry, the machines don't rotate, the shaft does. If your machine's rotating, you've got an even bigger problem. So here what's happening is as the shaft turns, there's low vibration, high vibration, low vibration, high vibration, low vibration for each revolution of the shaft. This gives me an idea of what is happening as the shaft turns. Here is some vibration, peak view again, which isn't very intuitive to look at. It's very useful, but it's not very intuitive. When I look at it on a circle plot, I can see that for a fair chunk of the revolution there's hardly any vibration, then suddenly spike, 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 lots of vibration just in one region. We get a bit of smooth operation and then a whole lot of spikes. Now, I would say, looking at this is from a bearing. Now, the circle plot doesn't know gravity, doesn't know where the load zone. I'm guessing this is the load zone of the bearing. So visually imagine this all happening at the bottom. So as the balls are rolling through the load zone, we're getting all this damage through the top of the load zone knot, and for some reason we're getting, as the ball maybe spits out, and we're getting some other damage at this point here. The circle plot is a unique way of looking at it. But the thing to understand, you might be still wondering, well, what is the circle plot? So imagine I've got just this simple vibration, and it happens to be, in this instance, 4 times running speed. So 1, 2, 3, 4 per revolution. Well, okay, it's a very simple example, but a circle plot reveals what's going on. All I'm doing is taking that time waveform and wrapping it around a circle. So, and you can see what's going to happen. Now it's much easier for me to see that once, twice, 3 times, 4 times per revolution, I'm getting this increase in vibration. It's more useful when I look at a case like this. Now this is just simulated simple data, but I've got mostly periodic data, but I got this one spike. So let's just pretend, if you will, that this vibration is the gears meshing together happily, and this is one bad tooth. So here's one revolution of the shaft, here is the one bad tooth. And when I wrap that around a circle, you can see it stands out more clearly. Now, in reality, this spike will be much greater in amplitude than the rest of the vibration, well, if it was a serious problem. But either way, we will see quite clearly that there is just this one impact per revolution. Earlier I showed you a case where there were 4 spikes in a row and then a little gap and then a 5th spike. In this case, we would have seen spike, 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 and a little bit further during the rotation, another spike. It would wrap around, and then all those spikes would lay on top of each other. A very useful analysis technique. Now, This isn't really an analysis technique, time synchronous averaging. It is actually a measurement technique which gives us some useful data to analyze. Now, normally when you analyze vibration, it is analyzed in the frequency domain. You are taking spectra and averaging them together. Earlier we saw the little simulator where we took the 4 chunks of vibration. I mentioned that we therefore collect 4 spectra. They get averaged together to average out the noise. Not remove it, just average it together. Time synchronous averaging works differently. Time synchronous averaging is where we average the time, those time records. But if we did it, okay, just before I say that, the time waveform I've got here, I've simulated by adding 1x vibration, there's the shaft rotation, 5x. Now you don't have any gears with 5 teeth, but let's just assume this is the tooth mesh frequency. Then I've got 7.2x. It's smooth vibration, but it's non-synchronous. It's not an even, an integer multiple of running speed. So let's pretend this is our bearing vibration. And then we've got noise. Now, if I look at just a whole lot of this vibration, and I grab one time record, which maybe it's at 2048 samples or whatever, there it is. Here's another one, there it is. Here's another one, there it is. We could create a spectrum of each one of these and average it, but if I want to use time-based averaging, then I would average all of those together, because that's not going to produce anything useful. It's just going to average all the information away. So instead, what we do is we synchronize the data collection to a TAC signal. We start on the TAC, we grab our 2048, and then we wait, and then we start again. And now what happens when we do that, and we look at our 3-time waveforms, they overlay very nicely. The variation is because of the non-synchronous vibration, the 7.2x, and the noise. So if we compare what we ended up with to just 1x plus 5x, it's the same. 1x plus 5x plus 7.2x is different, and certainly if we added the noise. Now, I've shown this with just 3 waveforms added together. Normally you need lots more than that to average this stuff out. But anyway, that's what time synchronous averaging is. In gearbox analysis, it's useful because gearbox vibration can be very complicated. It can be complicated by multiple gears and multiple teeth. But with this, we can hone in on just one set of teeth meshing together, and everything non-synchronous is averaged out. The bearing vibration and the other gears. So we might need to do this for each gear pair to get the data we want, but still we wouldn't be able to analyze bearings with this. But there is another technique called autocorrelation, and again, like all these things, we could take a long time to really understand this properly. The simple way of describing autocorrelation is, imagine if we took in fact that data that we saw here, and we did an FFT. The FFT would clearly show the 1x peak, the 5x peak, and the 7.2x peak. But the noise is just noise along the noise floor. Well, if I then did an inverse FFT, I would just end up with the 1x, the 5x, and the 7.2x. An inverse FFT is just taking that same calculation that took those time waveforms into the frequency domain, it takes you back out of the frequency domain into the time domain. And we can do it in such a way that we leave the noise behind, and we end up with a much cleaner signal. And that's what autocorrelation does. It has the effect of removing the noise. In this case, it would leave the 7.2x vibration in. And look, it would take a long time to explain this, and I think we've taken a long time. Let's just say that it's a very useful technique. It's very good when you have low frequency vibration that you want to highlight, like cage vibration or something like that. It's good for cleaning up data, but it keeps bearing vibration data because it doesn't matter that it's not synchronous. So, in conclusion, time waveform analysis very much complements spectrum analysis, as does phase analysis, but that's for another webinar. So, yes, you still need spectrum analysis, but you should be collecting the time waveform data too. Time waveform analysis can help you diagnose faults that would be difficult to diagnose with spectra alone. Time waveform analysis can help confirm a fault condition. So you may look at the spectrum and think, I think this is the problem. Toggle across to your time waveform. Ah, yes, thank you, that confirms what I thought. And finally, it gives you a good indication of severity, particularly for bearing faults, but also gear faults. Time waveform analysis helps you determine that there is a problem with the gear, and it gives you an indication of severity as well. Bottom line is, no vibration analyst should be without skills in time waveform analysis. I honestly believe that. So thank you very much for viewing this presentation. I know it's a bit of a long one. We do have a series of presentations called 9 Minutes of Knowledge, and you should come to our website and sign up for those. We have lots of presentations on just lots of presentations on reliability improvement and on vibration analysis. As you can see, I could talk for a long time, so I try to contain what I have to say to just 9 point something minutes, let's just say under 10 minutes. But of course, there's only so much you can say. So we've broken up the topics into little chunks, just little easily consumable chunks of 9 minutes. So please, go to our website and sign up for those 9 minutes of knowledge presentations, and you'll get them in your email. But anyway, thank you for viewing this presentation. I hope you found it useful. As I mentioned earlier, we do have lots of vibration analysis training classes all over the world in all kinds of languages using the sorts of simulators and animations you saw here and lots more. And if you choose to become certified, the certification is of the highest standing that there is in the world. The other forms of certification you get are no higher, and in some cases they are lesser because they're not accredited. And some don't even follow the standards at all, but that's another story. Anyway, thank you very much for viewing this presentation. I hope you found it useful. And feel free to tell your vibration colleagues about these presentations. Thanks a lot. Bye.